Water as an acid or a base. So it has the special ability to be something called amphoteric, which means a substance that can behave as either an acid or a base. So water is the most common amphoteric substances, but some substances with multiple hydrogens have the ability to act as either an acid or a base. An example of this would be something like H2PO4-. So it has the hydrogen, so it's able to lose hydrogens to act like an acid, or it's able to gain because it has that minus charge and act as a Bronsted-Lowry base. Ionization of water, water kind of auto-ionizes when it's with multiple waters in a solution into hydronium and hydroxide. So we kind of write this down here as the common way of writing the ionization of water. And then we have the Kw. So if you remember from equilibrium, we have this K thing, Kw. So it's the concentration of the hydrogen ion times the concentration of the hydroxide ion. So those square brackets stand for concentration. So we have hydrogen ion. Notice that we're in molarity for both of these. So at 25 degrees Celsius, the K is equal to 1 times 10 to the negative 14th. This is something that we're going to be using in some of our pH calculations. These two values are related to each other, so if one is increasing, the other is going to decrease. So when you multiply them together, it's always going to be equal to 1 times 10 to the negative 14th. So there's three options. You can have a neutral solution when the concentrations are equal to each other, an acidic solution if you have more hydrogen, or a basic solution if you have more hydroxide. So because the pH scale is such a small concentration, we use a logarithm to describe the pH, which the P stands for the power. So we have the pH, which is the more common one that you're probably used to seeing, which is the power of hydrogen, or pOH, which is less known and is the power of hydroxide. So using your calculator, you're going to press the plus minus key, depending on what concentration you have, press the log key, and then enter the hydrogen concentration. So on a non-graphing calculator I listed over here, most of you probably have graphing calculators. There are their own unique rules to significant figures with the pH. This isn't something that we're going to be focusing on a lot, but I wanted you to know. So the number of places to the right of the decimal for a logarithm must be equal to the number of significant figures in the original number. So for this first one, we have the hydrogen concentration, so we're going to calculate the pH. pH is equal to the negative log of the value you're given, 5.9 times 10 to the negative 9th molarity. So we're going to plug this in our calculator. So we're going to have 5 negative log 5.9 second e the negative 9th, and that will give us our pH of 8.22914. Now, because we have two significant figures in our concentration, we're going to have two decimal places, so we're going to end up with 8.23 as our pH. Now notice pH doesn't have any units. Whenever you have a logarithm, you always lose the units. The next one is pOH. It's the same idea, negative log of 2.4 times 10 to the negative 6th molarity. We're going to plug that in, and we're going to get pOH is equal to 5.62. You want to make sure you're being careful with your hydrogens and your hydroxides. You don't want to mix those up. So backing up for a moment, taking a look at concentration. So here we have the concentration of hydroxide. So we're going to use the equation Kw is equal to the concentration of hydrogen times the concentration of hydroxide. So we know Kw is 1 times 10 to the negative 14th. In this one we have hydroxide, so we're going to solve for hydrogen ion. So it's going to be 1.0 times 10 to the negative 5th molarity. So we're going to divide these two. We want to be careful when we're dividing. So we want to either be using the e function or, oops, I have a comma in there. Use the e function or the parentheses. So we'll get 1 e to the negative 9th. So we will, and again the units here are going to be molarity. So I wouldn't worry as much about sig figs here. So it'd be 1.0 times 10 to the negative 9th. And we're going to do the same thing for the next one, except we're going to be solving for hydrogen. So kW divided by hydrogen concentration will be equal to the concentration of hydroxide. So we're going to plug in the same thing. So we're going to get 1.00 times 10 to the negative 15. So you do need these zeros to be significant for sig figs. So we do actually have another formula, pH plus pOH is equal to 14. So we can rearrange this equation to solve for the pH or the pOH. So in this case, we're given the pH is 7.4 for blood, so we're going to take 14.00 minus 7.4, and that will give us the pOH. So we're going to get the pOH is equal to 6.6. So this is just another way to calculate and kind of go between one and the other. Because they're related, there's multiple ways that you're able to connect them. So the other way we have to be able to go is go from pH to the hydrogen concentration or hydroxide concentration. So what we're going to be doing, we're going to be pressing the second function, then log the plus minus key, and then enter the pH. So let's take a look at the example. We, again, are looking at human blood. So we're going to plug this into our calculator. We're going to have second log, it gives us this 10. So the negative pH, which is 7.41. And that gives us the concentration of our hydrogen ion. So the concentration of our hydrogen ion is going to be 3.9 times 10 to the negative 8th molarity. Concentrations always have a molarity next to them, while pHs do not have a unit. So we're going to take a look at the next one. We have a pOH of water in a fish tank. We want to know the hydroxide concentration. So we're going to do exactly the same thing. Why don't you try this one on your own? So the hydroxide concentration is going to be equal to 2.6 times 10 to the negative 7th. So again, there's 2 decimals here, so there should be 2 numbers in your significant figure. So what you would end up doing in your calculation would have been 10 to the negative 6.59 is equal to your pOH. Now if this question asked you for your H plus concentration, you would then use the kW divided by your concentration of hydroxide, which would be 1 times 10 to the negative 14 divided by the 2.6 times 10 to the negative 7th, and you would get 3.8 times 10 to the negative 8th molarity. So the question wasn't asking you for that. The question was asking you for the hydrogen or hydroxide concentration up here, but just sometimes that is a question. So that brings me to this graphic here. So you're actually able to start anywhere and calculate anything, depending on which direction you're going in, depending if you're given the concentration or the pH or pOH. I tend to use this one a little bit more often because the bottom one, it can be a little bit confusing using the kW, but either way it would give you the same answer. So why don't you try the learning check questions? So here you can see the answers. So the first 2 were straightforward. The third one, you first had to calculate the pOH, and then you could calculate the pH. The other option would be to use kW and kind of work your way around the problem the other way. Both would give you the same value.